Hello students. This question is presented by teacher Isa Al-Nabani. Today we will find the center of gravity of a triangular lamina with a non-uniform density. First, let's understand the physical meaning. A lamina is a thin flat plate. If its density varies from point to point, its center of gravity, or center of mass, is the single point where the plate would balance perfectly on a pin, taking into account how the mass is spread out, not just the shape. Think of it like a seesaw. Every small piece of the plate creates a turning effect, or a moment, equal to its mass times its distance from an axis. The center of gravity is the exact point where all these turning effects cancel out perfectly in every direction. Our lamina is the triangular region with vertices at the origin, at 0, 1, and at 1, 0. Its density function is delta of x y equals x times y. Notice the density is 0 along both axes, and grows larger as we move away from them, toward the hypotenuse. To find the center of gravity, we need three quantities: the total mass m, the moment about the y-axis for x bar, and the moment about the x-axis for y bar. Mass is the double integral of the density over the region. Each moment is the density multiplied by the distance from the corresponding axis, integrated over the same region. Let's find the equation of the hypotenuse first, since it will define the upper boundary of our region. It's the line connecting the points 0, 1 and 1, 0. The slope is the change in y over the change in x, 0 minus 1, over 1 minus 0, which equals negative 1. Using the point 1, 0 with this slope, we get y minus 0 equals negative 1, times x minus 1, which simplifies to y equals 1 minus x. Now that we have the boundary line, let's set up the region. We sweep a thin vertical strip from x equals 0 to x equals 1. For each fixed x, the strip runs from y equals 0 up to the line we just found, y equals 1 minus x. This gives us our limits of integration. Let's compute the mass first. We integrate xy over the triangle, with x from 0 to 1, and for each x, y from 0 to 1 minus x, integrating with respect to y first gives x times 1 minus x squared, over 2. Then integrating with respect to x, using the binomial expansion, gives a final mass of 1 over 24. Next, the moment about the y-axis, needed for x bar. We integrate x squared y over the same triangle. Following the same steps, integrating over y first, then over x, gives a moment of 1 over 60. By a similar calculation, integrating x y squared over the triangle gives the moment about the x-axis, needed for y bar. This also equals 1 over 60, since the region and density are symmetric when x and y are swapped. Now we divide each moment by the mass. X bar equals 1 over 60 divided by 1 over 24, which simplifies to 2/5. And by the same symmetry, y bar also equals 2/5. So the center of gravity is at the point 2/5, 2/5. Let's understand what this point really means physically. If you place a single pin exactly under the plate at 2/5, 2/5, the plate stays perfectly level, because the turning effect of the heavier mass near the hypotenuse is exactly balanced by the turning effect of the lighter mass spread near the origin. Move the pin even slightly away from this point, and the heavier side would pull down, and the plate would tip. This is why we call it the true center of gravity. It is the one point through which the entire weight of the plate effectively acts. Before comparing, let's see exactly where the number 1/3 comes from. For a plate with uniform, constant density, the center of gravity is simply the centroid of the shape, and the centroid of any triangle is just the average of its three vertices. Averaging the x-coordinates, 0, 0, and 1, gives 1/3. Averaging the y-coordinates, 0, 1, and 0, also gives 1/3. So the uniform centroid sits exactly at 1/3, 1/3. Now here's the geometric meaning of our answer. Because our density is 0 along the two legs, and grows toward the hypotenuse, reaching its maximum at the midpoint of the hypotenuse, the true center of gravity shifts away from the origin, toward that heavier region. That's why 2/5 is larger than 1/3, pulled toward where the plate is heaviest. This problem shows how integration lets us locate the true balance point of an object whose mass is not evenly spread. Keep practicing, and I will see you in the next question.